Hello guys, this is Code in Code and this is 18th lecture of this graph theory series part 1. And in this lecture we are going to see how we will apply depth first search, that is DFS, on a grid. So before we start the lecture, let's see what are the similarities between between a graph and a grid. You see, in a graph we have nodes, right? Same way in the grid we have cells are like nodes in the graph. Now graph also have edges. So what are edges in case of grids? Because if cells are nodes, they must be connected or disconnected, so there must be edges. So what are edges? So there are two different kinds of edges depending upon the problem statement. In the problem statement it will be specifically mentioned. Some of the edges are considered the sides of the cell is considered to be an edge, and two cells are said to be connected if they share a same side. So for example, this and these two cells are sharing this side, so these two cells are said to be connected by an edge. Similarly, this and this and this and this. For this there are two connections, left and down. So the cells are considered to be nodes and edges are considered to be sides. And in some problems they will be mentioning that sides are edges as well as corners. So if two cells are sharing a corner, that means they are connected by an edge too. So for example, this and this are sharing this corner. This and this cells, these two cells are not sharing any edge, but any common edge. They do not have any common edge, but they have a common corner. So sometimes what happens, they tell you that okay, sides are equal to edges. That means if two cells are said to be connected if they share a common side. And in some problem statement you will find that they'll tell you that two sides are said to be connected, either they share a side or share a corner. So these two important things are there to be considered before we start DFS on grid. So a cell in a grid is considered to be a node, and edge are either side or corner. So before we see how DFS works on 2D grid, let's see how DFS works on a graph. So see how DFS works is that you have node, and whenever you reach a node, this is a simple DFS. I'm assuming that you already have watched DFS, BFS and the previous lectures, and this is the course, and this is 18th lecture, so it is required you to watch the previous lectures as well, so you have idea, because I'll be mentioning some of the things that I have already discussed in past lectures. So of course you must have idea about that. So this is simple DFS code. What happens whenever you reach certain node, you mark that node as visited. So red is a kind of mark of visited. After that, in the adjacency list of current node, you would see every single node which is connected to current node, and if that node is not visited, that means you would make a DFS call to that node. For example, if you reach this node, what you would do, you would mark it as visited, and in the adjacency list of this node, this and these two nodes are connected. So you see whether this node is visited or not. This is where you are checking that, and if this is not visited, you would make a DFS call to that. Similarly, after DFS call of this node is completed, you will see whether this is also in your adjacency list, of course. So you will see whether this node is visited or not, and then if it is not visited, you would make a DFS call to that, and as simple as that. This is how DFS works in normal graph. If I show you how DFS work on grid, this is really easy. See, even though you may see that okay, the code is lengthy in case of grid, but it is shorter in case of normal graph, and still I'm saying that this is easy because there is surety of some things. Let me tell you what. First thing, you do not know whether how many nodes are there in the adjacency list of any node, and that is why we have to run a for loop, because it is not constant, it may vary. The number of nodes can be 1 in the adjacency list of certain nodes, and the number of nodes in the adjacency list of certain nodes may be 100 as well, depending about the graph. But here we know that okay, if sides are described as edges, then there are only 4 possible connections. for this node, that in the adjacency list of this node, this and these four nodes are directly connected to it. So you would make 4 recursive calls up, right, down and left. Similarly, same is true for every single cell in the given grid. First important thing, each node can be uniquely specified by a node number like this. If there are 10 nodes, we usually go with node 1, node 2, node 3, node 4. These we use as specifier. But in case of grid you if the grid is of size n cross m, then for each cell the unique specifier is the number of row and number of column. So if I'm talking about 2 1, that means I'm talking about this cell, because this is in the second row and the first column. So for each node we need we need its row number and column number, unlike in the normal DFS where we only need a node number. So what you would do, you would mark it as visited. As you can see, as the first thing you would do is mark the current node as visited. So if you reach certain cell, you would mark that cell as visited. After that, you already know that there are only 4 possible connections in this case, where we are assuming that common edges are considered sides are considered to be edges. So we have 4 different nodes, we have 4 different cells which we are connected to. So we'll see whether I can go up or not. So going up means going from xy going to x minus 1 yth cell. So first you will check whether it is valid or not. What is valid? Is valid is a function that will return whether the node you want to go actually exists or not. So for example, from here I wanted to go up, but there is no cell which is directly above this node. So it will return true or false based on 2 factors. First, it will check whether the cell you want to go even exists or not. If the cell doesn't exist, it will return false. Otherwise, it will check for the second condition, that is whether that node is visited or not, like this thing. So I'll try to go up. So is valid will check whether the cell directly above the current cell exists or not. If not, it will return false. If it returns false, I cannot make this DFS call, of course, right? If it otherwise, if the cell exists, is valid, we check for the second condition, that is if whether the cell you want to go actually is visited or not. If that is not visited, it would return true, so you can make DFS call to up. Similarly for right, down or left. This is how DFS works in 2D grid. If I show you example, suppose we made a DFS call to cell 11. So you mark the cell 11 as visited, and blue color shows you the status of visited or unvisited. Blue is visited, the rest the white colored cells are unvisited. So you try to go up. So is valid function will return false because there is no node, there is no cell directly above you, so it will return false. Now you try to go right. Yes, you can go right because the cell on the right actually exists, as well as it is unvisited. So from there you would make a DFS call to cell 21, not 21, I guess it is 12. So you would make a DFS call to 12. Now this indicates that from this cell you made a DFS call and you made a second operation. Second operation means going right. When we come back from DFS, when DFS call of this node as is completed, so you would come back and then you would continue your operation. So you were at this point at second operation, so you would go to perform this and this. That is why there is 2 to indicate the last performed action. So you are at this node. Here you would try to do again the same thing. You would mark as visited, so this is blue. You try to go up, but that's not possible. You try to go right. So from 12 you would move on to 13. 13 cell will try to go, and the last perform action was 2 because we went to right. And 12, when you reach 12, you'd mark it as visited. You try to go up, that's not possible, that cell doesn't exist. You try to go right, that is not possible, the right cell doesn't exist. So you try to go down. Yes, that cell exists, and as well as it is not visited. So you would make you'd perform third operation, and you basically you made DFS call to down cell. So you are here. Similarly, everything will be performed here. Now from here you would go down, you try to go up, not possible, you try to go right, not possible, you try to go down, not possible, you try to go left, that is possible. So you'd make a DFS call to left, which is fourth operation. So fourth operation is performed. This is just to show you the what was the last operation performed, so that we can continue from there when we come back from DFS call. Similarly from here you try to go up, that is possible because up cell exists as well as it is not visited. So you'd come here, you try to go up, left and right, all of three are not possible. So check for up, right and down, all of these three are not possible for this cell because up is visited, right is visited, down is visited. Only option is to go left because this is the fourth operation. So you'd perform the fourth operation. Similarly for this node, you try to go up, not possible, right, not possible, down, yes, that is possible. So you make a DFS call to down cell, and this cell will try to go up, not possible, right, not possible, down, not possible, left, not possible. So this node, from this cell you directly return to the cell which has made DFS call to this, and that means we will return to this cell. Similarly from here you will return, last operation you perform was this, so you would continue your code from there. So you try to go left, that is not possible because left node is already visited, that is why your work here is completed. So you would return to the cell which has made DFS call to you. So you return to this. Similarly everything will happen and every node will simply return to the cell which made DFS call to them. So the order was order of visit was 1 1 1 2 1 3 2 3 3 3 and so on. Let me show you, just let me show you the code. So this is the code. I hope this is visible. So you see in the main function we are only reading n and m, that is number of nodes and number of rows and number of columns. After that we are making a DFS call to node 1, cell 1 1. After that this is visited array to store the status of each cell, whether that cell is visited or not. Is valid function here will take two parameters x and y, and we are assuming all of the rows are numbered from 1 to n and all of the columns are numbered 1 to m. So if you want to go row which is smaller than 1, and if you want to go row which is greater than n, that means you are going outside the grid, that means you will return false. Similarly for y, and if this condition doesn't hold, that means you are going to a cell which actually exists, that means you would see whether the cell is visited or not. If that is already visited, you would again return true. You would return false, that means you can't visit the cell you are requesting for. And if these two conditions doesn't hold, that means you can simply return true, that means that cell exists as well as that is not visited, so you are returning true. And in the DFS function, you are marking at visited, you are trying to go up, right, left and down, depending upon is valid function, status of invalid function. So if I show you, if I go for 3 cross 3, you see we went to, let me show you, if you remember, from 1 1 we went to 1 2 and then 1 3, then 2 3 3 3 3 2 2 2 2 1 and 3 1. This was our order of execution. The order of execution may change, like the DFS, as you may already know that order of DFS may change depending upon the way you are calling recursive DFS function calls. Now this can be done in a smooth way. Instead of writing 4 different conditions, you may think, okay, where we have a condition where corners are also considered as edges, that in that case you would have to write 8 different conditions of is valid. Well, that is not very true. What you can do is, a better way to do it is create a dx array which will define your x direction. And you see, if you want to go up, you are decreasing 1 from x, so basically you are adding -1 to x. Then the next call was to go right. In that case you are adding nothing in x, so 0. Similarly for down you are adding 1 to x, so 1. This is I'm creating an array. And then if you want to go left, you are adding nothing in x, so 0. Now similarly for dy, change in y. So when you wanted to go this was for up, I guess. When you wanted to go up, you added nothing in y, so 0. When you wanted to go right, you added 1 in y, that is why 1. When you wanted to go down, you added 0 in y. When you wanted to go left, you added -1 in y. After that, what you can do, instead of writing all this, let me just comment it out. You can write 2 or 3 lines of code. Let me show you from here. Since you have 4 different directions, so run a loop from 0 to 3, because 0, 1, 2 and 3, these are all of your possible directions. So if is valid x plus dx of I and y plus dy of I. If that is true, that means you would make a DFS call to x plus dx of I and y plus dy of I. That's all. Instead of writing whole this code, you can define the direction. And remember, this was we added -1 when when we wanted to go up, right? And we added 0 because 0 in y because we wanted to go up. So these two must match. This is what you did in x when you wanted to go up. This should be also what you do what you did in in y when you wanted to go up. So these two combined define your going up, these two combined define your going down, right? These two combined define your going down, and these two define going left. So you can do this and the code still will run fine. So you see, we have reduced the code quite a bit. Now if I show you the compile, and again if we run a DFS for 3x3, we'll see there is no change unless I made some errors. Come on, yes. So let's run for 3x3. You see 1 1 1 2 1 3 2 3 3 3 3 2 2 2 2 1 and 3 1, which means it is running fine. So this is how you apply DFS on 2D grid. In the next lecture we will see how DFS is used to count the connected component even in a given 2D grid, and we will use, of course, DFS that we have just studied. So this was all for this lecture. Thank you guys for watching. Until the next video drops, keep coding. Thank you.